Okay, so we're going to now have a look. You're right. Okay, we're going to start this next bit now. So we're going to now look at things that are connected together using pulleys instead. So a pulley, this is a picture of a pulley that I just got from the internet. You've probably seen these kind of things. I mean, not very much in real life, but it's just basically a kind of a rotating circle with a piece of rope going over the top of it. And the idea is that the rope can then sort of move over that pulley nice and smoothly so that so that things can sort of rotate and move around them. There's a couple of things I want to talk about in this situation that we've got here. We will have two particles that are either side of this pulley, and you should be able to make a prediction about what will happen in that scenario on that far right-hand side. What do you think will happen?
The bigger one would go down.
Yeah, the bigger one would go down, which means that the smaller one would have to go up. So if you just kind of think about that as though my hand is like the pulley, and then you've got the bigger mass on one side, which is the keys, and then the other side is just the other end of the lanyard. What you'll notice when I release this is that the keys are going to go down towards the floor, and the bit that my hand is holding onto, that I'm holding to release, that's going to move up while the other one moves down, like that. Okay, my hand got in the way. And we're going to be sort of modelling situations that look like that, where one thing is moving down and the other thing is moving up. So it's just going to be going like that kind of scenario, okay? My wrist there that the string was passing over is like the pulley. My keys was like one of these particles, and the little connecting bit on the lanyard was like the smaller particle that we have there. One thing to note so far is the particle that has the higher mass is the one that will move down. The one with the lower mass will move up. They can't both move up and they can't both move down because they're connected by a string. So in this bit, I've got a couple of questions that I wanted us to think about to begin with. Why can't we just model both particles as a single particle as before? Like, you know, when we did the lift, we zoomed out and we looked at the whole lift. When we did the car and the trailer, we zoomed out and we looked at the car and the trailer. Why can't we look at them both as good? Because they're moving in different directions. They are moving in different directions. Under what conditions is the tension in each part of the string the same? This is those kind of modelling sorts of questions that we have here. So under what conditions is the tension in each part of the string the same? This is... no, it's actually even more general than that. This is when the pulley... when the pulley is smooth. And I'm going to tell you a bit more about what this means in a second, okay? If the pulley is smooth, meaning that there is no friction, it means that the tension on both sides of the string is the same. Now, the reason that that is true is because if this was rough, then one side might be pulling down quite tightly, but if it's getting stuck somewhere, one side of the string may be really taut and really tight, meaning a high tension, while the other side of the string, where it's snagging and getting caught on the pulley, would be quite loose and not as tight, so would have a lower tension. But if the pulley is smooth, there is no snagging or getting caught or rubbing against the pulley, so the tension on either side of the pulley will be equal. It's this idea of things snagging and getting caught. If you imagine that there was a mass here and I was going to pull down really, really hard on this side, if this was rough, like very rusty and wouldn't rotate very well, this side of the string would be really, really taut and I'd be really tugging on it very hard, whereas this side may not even be moving very much because it's so rough at the top. So by being smooth, the tension on both sides of the string is equal. If they ever ask you about that, what does it say that the pulley is smooth? That means that the tension on each part of the string is the same. Okay? So we're going to now actually do a question here, and we may do another sort of another question that we don't fully complete, and then that should us be pretty much finished for this lesson, and then you're going to do some of these for homework, and we'll do another part on it next lesson. So it says particles P and Q of masses 2m and 3m are attached to the ends of a light inextensible string. The string passes over a small, smooth, fixed pulley, and the masses hang with the string taut. The system is released from rest. and we're going to do various things. We've got 5 different things that we're going to try and do here, and I think I've given you an extra page to do this in your booklet, so you're going to need to make sure you take out, sorry, I just mean like an extra section underneath it, so you're going to need to space out your page carefully. I mean that you've got like a blank page where I would normally have, yeah? Okay, so the first thing that we're going to do here is I'm going to draw a diagram. Now, to draw a pulley, the best way to draw a pulley is just literally just to draw it as a circle, and then to draw it as like the string kind of going either side of it. That's probably not the best way of doing it, actually. I prefer it a bit more like this. There we go. Sort of, apart from this is a circle here, and we've got these 2 particles like this. So here is our pulley. You don't need to label this if you don't need to. That's the pulley. That was like my wrist. The string here was like my red lanyard. And then this is like the keys, and this is like the other side of the end of the lanyard that had the little clip on it, okay? And it says that they've got masses of 2m and 3m. So this one is going to be particle P. This one is going to be particle Q. So this one has a mass of 2m. Now, if its mass is 2m, what is its weight? 2mg. And so the other one's weight must be 3mg. Now, by using the letter m here, I'm keeping it very general. What I'm really saying is the ratio of the masses is 2 to 3. It could be 2 kilograms and 3 kilograms. It could be 200 kilograms and 300 kilograms, or it could be 40 kilograms and 60 kilograms. The m is the thing that means that I'm just keeping it in the kind of ratio. They might do questions that have m in it. They might do questions that just have numbers. But I wanted to show you one that had an m in it. Okay, and we're going to try and write down an equation of motion for P and Q. Well, I think before we do that, I want to kind of finish off what these diagrams might look like, okay? Concentrating on this particle P, if you imagine that you were this particle P, obviously we know that your weight, you can feel your weight, but what else can you feel if you're hanging from a piece of string? You can feel the tension, okay? Hassan, which direction do you think the tension would feel like? If you were this particle, would it feel like it was pulling you up or pushing you down? It would feel like it was pulling you up. So this tension here is going to be going upwards, right? And then, Ishak, for this particle Q, will the tension be going in the same direction, going up as well? If you feel like you're hanging from a piece of string, you feel like your weight, does it feel like the string is pulling you up? Yeah, it does, doesn't it? The string is also pulling you upwards like this. So if you literally imagine that you're hanging from the string, it feels like the tension is pulling you upwards on either side. Now I want to add a couple of extra things to my diagram. We know which way these things are going to move, okay? Ibtiaz, which way are they going to move?
Up or down.
Which one is going to go up and which one is going to go down?
And 3 is going to go down.
The 3 mg, the Q particle, is definitely going to accelerate downwards. And the P particle is definitely going to be accelerating upwards. I know that because 3 is bigger than 2. So that one is definitely going to want to move downwards, yeah? An equation of motion. An equation of motion is posh language that just means F equals ma. So you need to write that down. If it asks you to find an equation of motion, it's asking you to do F equals ma. Okay? So for part A of the question, I'm going to have a look at particle P. So I'm going to ignore this one completely. I'm just going to look at particle P, and I'm going to resolve upwards. This is for particle P, using F equals ma. I'm resolving it upwards because that's the direction that the acceleration is. So when I resolve this, what should my resultant force look like? T minus 2 mg equals the mass, which is 2m, times the acceleration. This here is my equation of motion Now I'm going to do it for the other particle, which is q, and I'm going to do F equals ma, but which direction am I going to resolve? Up or down? Why? I agree with you. Why? It's going downwards. We need to do it in the direction of the acceleration. So we're going to resolve it going downwards. So I get, in fact, Hassan, what do I get when I resolve this one downwards?
3 mg minus t.
Good. 3 mg minus t equals 3 ma. And this one is my equation of motion for particle q. So I've done the first part of the question now. I've done the equation of motions for both of them. I've done F equals ma and I've done F equals ma. And I'm now going to, for part B of the question, try and find out the acceleration. And for part C, I'm going to try and find out the tension. I'm just going to put a box around this because this is, without doubt, these two things here are going to be the most important things we're using right now. What do you think I'm going to do with those two things that I've just boxed to try and find out the tension or the acceleration? Yeah, simultaneous equations. I've got two equations and I want to find out tension and acceleration. So I'm going to try and solve these two equations that I've got here. Can anybody spot a really nice, quick technique that you could use that would combine these equations? You could make them both equal to t, which I'm more than happy for you to do. You could, that's what I think Arafel is saying, is make t the subject. There's a quicker one that you could do. I think there's even quicker. If I take this one as number 1 and this one as number 2, I can add them together. Now, if you want to make t the subject and solve the equation, I don't mind how you want to do it, okay? If you can't add them together, in other words, if you don't have a t and a minus t, you've done it wrong to begin with. Your equations of motion are wrong. Notice how this one has got t minus and this one has got something minus t. It's because of the directions that we're resolving them in. So you could solve them in a different way. If you wanted to, you could make t the subject here and you could substitute it in. Or you can just add these two equations together. Adding the equations together should always work to cancel out the t. So when I add these together, I have t minus 2 mg plus 3 mg minus t equals 2 ma plus 3 ma. So what's the left-hand side? mg. So I get mg, the right-hand side, is 5ma. Now I can cancel out from both sides the m, which gives me that the acceleration is a fifth multiplied by g. A fifth g, which you may sometimes see written as g over 5, which is 9.8 divided by 5, which is 1.96 meters per second squared. I like this answer, I like this answer, and I like this answer. Sometimes they will give you this as the acceleration. They won't give it to you as a number, but that's fine. We're happy to use g. G is fine for us to use. And now for part C of the question, I'm going to find out what the tension is. Which equation looks easier to find out what the tension is? 1 or 2?
1.
I think 1 looks easier. So if I use equation 1 and I rearrange it, I can see that the tension is 2ma plus 2mg. Well, the acceleration, seeing as I've got a g here, I think I'm going to use which one? Number 1, number 2, or number 3? Of these 3 accelerations I've got, which one do you think is the best to use for substituting in? I think number 1 is probably the easiest. I don't want to use a number because I've already got g and there's a g here, so I'm going to be able to simplify that nice and quickly. So I've got 2m multiplied by the acceleration, which is a fifth g, plus 2mg. So that's 2 fifths mg plus 2mg, and 2 plus 2 fifths, not 2 piths. 2 plus 2 fifths, let's do it as a fraction. 2 plus, I could do this in my head, is 12/5 mg. So the tension is 12/5 mg. I'm sure there's probably something you're probably saying to yourself in your head. Anybody saying something to their head and they want to tell me what it is they're thinking? Yeah, what's the value of m? Why have we got m in the answer? This is perfectly fine. This is perfectly fine to have the tension in terms of m. It's absolutely fine to have it in terms of m. The acceleration has got nothing to do with the value of m. But if you go back to this diagram for a second and you think to yourself, do you remember I said, oh, this could have been 2 kilograms and 3 kilograms, or it could have been 2,000 kilograms or 3,000 kilograms, depending on the value of m. This is if m was 1. This is if m was 1,000. Doesn't it make sense that the tension is related to the mass? Because the tension is how tight the rope is. If these were tiny little ones, 2 kilograms and 3 kilograms, the tension is going to be 12/5 g. But if it was 2,000 kilograms and 3,000 kilograms, it would make sense that the rope would have 12,000 over 5g. It would make sense that the tension would be much, much higher. So people often get to this stage here and they think, whoa, I haven't finished the question properly because I've still got my answer in terms of m. But that's okay if it makes sense for it to be in terms of m. So we're nearly finished with this question. Let's actually go and investigate what I've said we've got to do now. Find the force exerted on the pulley by the string. So this is interesting. We're now going to be changing this around. We're looking at the force exerted on the pulley by the string. Well, this means I need to look at a different part of the diagram. I'm going to add something to this diagram in red, and then I'm going to redraw it at the bottom of the page. These forces that we had over here were the forces that were acting on P. These forces here were the forces that were acting on Q. I want to know the forces that are acting on the pulley. So if you think about the pulley for a second, which was my wrist, what does my wrist feel like this? Which direction does it feel like the string is acting on it? Downwards, yeah. I can feel on my wrist right now, I can feel both sides. I can feel a pulling downwards here, and I can feel a pulling downwards here and here. And what do you think the top of my wrist is feeling? An upwards force. It's feeling a normal reaction at the top of my wrist. But it's not, it doesn't mean that it is light. I'm not feeling the weight of the string. I'm feeling the tension inside the string tugging down on my wrist, if my wrist were the pulley. Now, you may not like to add this to your diagram. It may be too complicated for you when you look back at it, which is why I've done it in red, and I'm going to draw a diagram separately at the bottom of the page. So when I do part D of the question, which I will do, I'll stick with doing it in red so it kind of makes sense. I'm now going to look at the forces on the pulley. So we have, there's the pulley. The pulley is feeling string pulling it down on this side. It is feeling string pulling it down on this side. It has to still be tension because it's the same string. And it's also reacting to that, and it's asking for, that would be the reaction force. We want to know the force exerted on the pulley by the string. So we're actually interested in these forces here. This is the one at the top I should have labelled maybe. This is the normal reaction at the pulley. And these are the ones we're going to find out. So the force exerted on the pulley by the string, well, there's two things the string is doing. It's not just tension. There are two tensions that are pulling downwards, one on the left-hand side and one on the right-hand side. So the force exerted on the pulley by the string is 2 t. It's this t and this t added together, which is 2t, which we know is 2 multiplied by the tension, which is 12/5 mg, which is 24/5 mg. And if the question said, find the normal reaction at the pulley, well, the normal reaction must be equal to the force that's being exerted on it, because they are equal and opposite, Newton's third law. Second law, third law? I can't remember what I said earlier. I can never remember them. So the normal reaction, as an extra question, if they said find the normal reaction, that's the same thing as finding the force exerted on the pulley by the string. So I'm going to just do a little extra bit that's in brackets here. The normal reaction is 2t, which is 24/5 mg. They must be equal to each other because it's in equilibrium. That pulley is not moving anywhere, okay? We're nearly there. You've done really well today. I'm just going to go to part E. Find the distance moved by Q in the first 4 seconds, assuming that P does not reach the pulley. So we're going to try and find out how far does this one move in 4 seconds. We're assuming a couple of things. One of them is that P doesn't hit the top, because that's what we're going to investigate next lesson. And one of them is it's not going to hit the floor. Okay, we're imagining it's quite high up, it's not going to hit the floor. So let's actually just do that last bit. Any suggestions of what we think we're going to do for part E? Suvat, good. We're going to do Suvat for particle Q. Suvat for particle Q, we're going to say that its acceleration is 1.96. We're going to say the amount of time it takes is 4 seconds. What else do I know about the particle? What's the U? Good. A U is 0 because it starts from, it says it gets released from rest. And so the distance that it's travelled is the thing I'm looking for, which is S. What connects those 4 together? Good. S equals ut plus a half at squared. So the distance it travels is 0 times 4 plus a half times 1.96 times 4 squared. The distance it travels in those 4 seconds is 0.5 times 1.96 times 4 squared. It travels 15.68 metres, which we round to 15.7 metres to 3 significant figures. So it's going to have to be quite high off the floor for this to happen. What we will be investigating next lesson is things like it crashing on the floor and what happens afterwards. Now, I'm going to ask you to do a couple of these ones as practice for homework. Well, I know you do want to go to lunch. I want to go to lunch too. I'm going to ask you to do some questions for the next exercise, but I'm going to ask you to not do like part E or part F or part D. So make sure you read the Padlet really carefully, because there are some questions we're not prepared to do yet. We don't know how to do them. So you must make sure you read the Padlet really carefully there. Well done today.